So, I welcome you all for today's talk. We are very happy to have Dr. Somnath Dutta. He is one of the pioneers in cryo microscopy, and this cryo microscopy has got Nobel Prize in 2018, 17, and it's a very versatile technique. Little bit of about Dr. Somnath. He did his PhD at National Institute of Cholera and Enteric Disease, which is the ICMR Institute at Kolkata, and that's in 2000, from 2006 to 2010, and at that stage itself, he has started using microscopy. After that, he did a postdoc at University of Michigan from 2010 to 2016, and University of Michigan is well known for for its biophysics and related stuff. It's a big center for in that sense. And then 2016, he joined IISc as assistant professor, and he is promoted to associate. Now he's associate in 2002, and his research is quite expansive in nature. But I'll just name some of them: post-pathogen interaction, structural biology, cryo, and more importantly, he has established a national facility for cryo-electron microscopy. And if time permits, we'll try to see this facility. Okay, but let's hope. I'll just ask Dr. Somnath to come on and really thank you.
Thank you. Hello everyone. First, I want to thank Professor Partho for inviting me. He was telling me last 3-4 months that I should not come here and give a talk. I cannot manage it, but finally I'm here. So, do I know the background of you guys, that how many biologists are there? And okay, so here I'm trying to make it very simple. Whenever I'm taking any class here, so I try to make my presentation like that. If you guys want to stop me, raise your hand and stop me. Don't wait until end. It will be very difficult to go back and explain. So immediately I'll answer your question. Okay, so now today's talk title, I mentioned that. Okay, so focus the electron beam using electromagnetic lenses to visualize the biological samples. So from here you can see that there is a two terms that is called that electron beam and as well as electromagnetic lenses. And if we combine these two, anyone can imagine that we are talking about the electron microscope, because we have a electron source and then we have electromagnetic lenses and we are trying to visualize the biological sample. So here I just want to add one small thing. So there is a wrong concept in all over India. You will get microscope everywhere. In every university, probably there is a microscope. But whenever any biological sample, you will take it and you will go and try to check it. First thing it will come to you, no, you cannot use it because it is for natural science sample. 300 kilo microscope you cannot use, but 300 kilo microscope is good for biological sample also. You just have to know how to use it. Okay, so today that is the reason I make my talk in such a way so I can go through one by one components of the electron microscope, and it will be easy to understand what I am talking. Okay, I'll just stand here and then. Okay, so this is the history of the microscope in short. In this short time, I cannot explain all the microscopy, how this microscope is developed from one stage to other stage, but we should remember that. So Galileo in 1609, he first developed that microscopy thing. So there is a tunnel and they put some kind of glass lenses and try to see the planet, stars, the moving object like that. So that was for the first microscope we have. Then, then Anton Leeuwenhoek, that is the first microbiologist. He is the microbiologist who used a light microscope to visualize the bacteria, and this is we call one of the first microscope which we can use for life science purposes. Then there are multiple microscopes, light microscopes are coming, that okay, compound microscope, more modified, sophisticated microscope, and nowadays you can see there are so many microscopes like that, fluorescence microscope, quantum microscope, single molecule imaging microscope, all are depending on light microscope. The light is the source, and that will help us to visualize the sample. Now, the question is, can we use something else to visualize the object? How do we decide? Okay. And the light, another easy thing is that we can use the glass lens to converge the light or diverge it. So that means we can focus the light. If I come to the next, okay, so if we go to the next slide, you can see this is the electromagnetic spectrum of all these waves. So here you can see this is the radio wave, then it is coming the microwave and the infrared wave, all a very long wavelength. So it is coming radio wave, if you consider it is coming in meter. Then microwave and infrared. So visible light, it is coming within 400 to 750 nanometer, shorter wavelength. But it is good for our eye. And if we just click this visible light, we can see all these different colors. And that is the reason we are using this thing for the fluorescence microscopy also, that you are using different kind of filter, you are blocking different light, and then you can see. But all depends on this range, within this range. Okay, after that, we are getting that UV. UV, the wavelength is coming within 100 to 380 nanometer. After that, we are getting X-ray and gamma ray. Then where we can get the electron. So generally, electron will come somewhere in between gamma ray and X-ray. I'll come to that point again. So here, when you can see, we are going to this direction, our wavelength is shorter and shorter and shorter, and energy is increasing. So energy increase, that is really good, that ray can penetrate through any sample. So whenever we are talking about electron microscope, first thing it will come to our mind, that is called the transmission electron microscope. So whatever source we use, that should transmit through the sample. So if we don't have enough energy, it cannot transmit. That is the reason we are using that electron, which can transmit to our sample, and we can see, we can visualize it. Now, so here, these are three types of rays I mentioned. That is the visible light. As I mentioned, that visible light is not damaging. So we are all moving around here within the visible light. Nothing is happening. UV is dangerous. Nowadays, people are talking about that UV can damage, it can create cancer and other things. It can damage the DNA also. But here, visible light is very good. That is not damaging at all. Easy to focus. Eye is a wonderful detector, but long wavelength, so penetration power is less. Now it is coming to the X-ray. The small wavelength, good penetration power. That is the reason when there is a broken bone or something, we are using the X-ray, and we are using the lead cover the rest of the part, and then X-ray is going through that, so it can go through our lipid, fat, or protein, everything, and then we can see the bone if there is a fracture or not. But it can damage the sample because it has a lot of energy. That is the problem. Now we can talk about the electron. That is a small wavelength. I am talking about the picometer range, and it can also damage the sample because wavelength is smaller. Poor penetration power than X-ray. Okay. So now I am telling, okay, this is a picometer range, the wavelength. How do we believe it is a picometer range? We have to calculate something, right? So best way to calculate these things, that this is the formula where we can take this one to calculate. How do we get this formula? So if you just remember the de Broglie's equation, that okay, we have a lambda, and this is a Planck constant, and this is the mass into velocity. Okay. So now, if we just consider any electron, the potential energy and kinetics energy will be equivalent. Okay. So from here we can get this V. So if you just take it that EV and this will be M and this will be half. Okay. So here V is the voltage, E is the charge of that electron, mass of the electron, and V is the velocity of the electron. So I'm just trying to get this V from this equation and I'll replace it here. So if I just replace it here, so what will get it? You will get it 2EmV. Okay, so it is depending on mass of that electron, charge of that electron, Planck constant, as well as that voltage. So here we know all of these values that, okay, what is the mass of that electron? What is the charge? And then Planck constant value, joule per second. If we just replace, it is depending on this voltage. Okay, so the lambda is inversely proportional with your root square of this voltage. So if voltage will increase, it will decrease the wavelength. So generally, electron microscope, you will get it different voltage. So you will get it 120 kilovolt, you will get it 200 kilovolt and 300 kilovolt. Okay, so when voltage will increase, your lambda will decrease. And from there, if we just replace all this value, from here we can calculate generally for 200 kV microscope, your wavelength of an electron will be 3.88 picometer. For 200 kV, it will be 2.72 picometer, and 300 kV, it will be 2.24 picometer. Now, as I mentioned that early days, even last 7-8 years also, I faced a lot of problem like that, okay, you can use lower voltage for biological sample. You cannot use a 300 kV for biological sample. But 300 kV is good for biological sample because your lambda will be smaller and penetration power will be much higher. And that is the reason most of the cryo microscope you can see in a good condition, the 300 kV microscope people are talking about that we want a 300 kV microscope. Okay. Now, here I'm just showing you some of these electron microscope. So this is Dr. Ernest Ruska, the first electron microscope in 1933. So he was a physicist and he developed this microscope and he got Nobel Prize later in 1980 or 82 sometime. And those are the microscope we have in our biological science. In 1980, this is a geode microscope where you can see there is no computer that time. Definitely computer will be not there. So we are just using a plate camera, that big plate camera and photographic film to image. And then we have to develop all of this. So even when I started my work, I did that thing in a regular basis. So I was, taking all this film, then I developed those things, and then we can see the images. So I can tell you one funny story. So many of you will do PhD, or you don't know that time your future also, even when you are doing masters also. And sometimes we are also getting frustrated, right? So when I was doing this thing, and regular basis I am developing all this thing, sometimes I'm thinking, okay, I'm doing PhD, I don't know what is going to happen. Then I thought, okay, one thing I know that I can do it. I can develop film, I will open a shop and I'll develop negative. Okay, so that is the thing. It is coming to everyone's mind. It is not like that I am exceptional, or so you guys will also be sometimes frustrated and will think that okay, so if that will not work, I have to find a different way. So those are the old days when we are using the photographic film, and then we develop those things, and then we are going for data processing or whatever we want to do. Then we have a new system where we have the computer attached and we have a CCD camera, and it is much easier to visualize your sample immediately. And then now we have this sophisticated machine where you can screen multiple grids in same time. Now here I want to show you one more thing, that is, one of these, horizontal electron microscope developed by Professor Somnath Dutta in SIMP, Sahara Institute of Nuclear Physics and University of Calcutta. It is in 2 years they built this entire thing. But after that, there is no initiative, so we cannot make this microscope here. Most of the time we have to, buy it from outside India. So here, this is just a normal 120 kV electron microscope. As I mentioned, there is 3 types of possibilities here. Is there based on that accelerating voltage, how they are pulling the electron. And this is a schematic diagram, very simple schematic diagram. We have a electron gun, then we have a anode, then we have 2 condenser lens, objective lens, and we have a sample here. When the electron beam will passes through that, we'll get a 2D object, 2D image of a 3D object. This is, you can see how electron beam is passing through this sample, right? Just like X-ray, and then it is giving you the image. That is the reason it is called the transmission electron microscope. There is another electron microscope is coming, that is called scanning electron microscope. In that scanning electron microscope, electron beam will not transmit. It will just, from the surface, it will reflect and will just collect that. So I'll come back to that point again. There is a one electron called backscattered electron, and we'll capture that backscattered electron for this. We'll capture that signal for scanning electron microscope. Okay, so this is a same microscope where you can see all the details here. So here you can see multiple knobs are here. The aperture as well as the lens system is connected here. So those are the old setup. That's why you can see all of these things and you can manually control. In most of the recent microscope, you will not get this kind of thing at all. So everything is controlled by computer. And yeah, definitely one thing is that when manually you can do something, you have more control. You can do mistake and you can learn from there. But now things are much more sophisticated. Computer will do automatically. So if there is any problem, it will lock the system. You have to call the system. You cannot do what you cannot fix. So here, but it is good to know the system, how it is connected. So here, in any light microscope, if I just, okay, I have one small question. So here we are talking about electron microscope, and we have the multiple lens system. If you just go here, the condenser lens 1, condenser lens 2, then objective lens, intermediate lens, and projector lens. And that is giving us the image, a very magnified image. So it is very simple if we just consider, if we don't think too much. So we have something light source, it is coming, and there is a crossover point. If we just use more and more lenses. So here, if we just consider this is one lens, and then second, and then third, then fourth. If we just go like that, you can easily magnify something. Then you can see any small things. Then that is true for the light microscope also. Right? Why do we need this electron microscope? Why do we need to make this complicated? We can just use a simple light microscope and add more and more and more and more lenses. We'll make a microscope like a, 3-story building. We'll just put lenses and then we'll magnify everything. And then at the end, for a, if you have a graphene, you can see all the carbon atoms if you just gradually magnify it. Cannot? Why not? Huh? What aberration? Aberration will be there. That is correct. Definitely, there are 2-3 types aberration will be there. But with aberration, we can also image, right? Even in electron microscope also, all the aberrations are there. But why we cannot do? That is my question. One is that wavelength of that light, right? That is we are talking about. There is a limiting factor that if you consider the resolution of, if you remember Rayleigh's equation, radix, how we can calculate the resolution. So if we ask you what is the resolution, so if you consider that, okay, one car is coming in a highway and we are in a far, so you cannot differentiate the two headlights, right? After a certain distance, when you are very close, you can see that two headlights are separated. So Rayleigh's equation is talking about the same thing. When there is a 2 point, the minimum distance where they can isolate it from each other. They are not merging together. That distance is called the resolution. And that resolution is highly depending on this lambda. And that is the limiting factor here. The electron microscope, the lambda is smaller, and that is why resolution is much better. And the second one is the penetration power, right? These two things. That is the reason even if we add 200 glass lenses, we cannot make it. And we cannot get a very high resolution images. And another thing, what you told, that is very good answer, that aberration. I'll not say aberration, that is whenever you will get an image, eye is a wonderful detector, right? Whenever you will take an image, and when that image will come, always remember that any object, that if we have an image, and it will be always object is cross product of point spread function. The point spread function is a blurring effect. And that way, even first image, whatever image you are getting here, it is already blurred by this point spread function. And that will just amplify again and again and again. And at the end, you will not get any good image. Okay, so here this is the same schematic diagram where you can see that this is the electron gun, and then multiple lens systems are there, and then we are getting the image. Here total 6 lens systems are there. So this is condenser lens 1 and condenser lens 2. Those are connected with the intensity and changing the contrast. Specifically, I can tell this is the plot size. We can regulate how much electron we want. Then objective lens is connected with your focus, how we can focus the electron. And then those lens system, we can magnify the image. Now, here I'm going to focus more in the electron gun and then magnetic lens, because those are the things different from your any light microscope. What is the source, that electron gun? Okay, so generally this electron gun, we have 3 different types. I'll talk a little bit about this one and then electromagnetic lens also. So here, if you look at this electron gun depends on that how much. So all the time, these electron guns are any metal, in that it will be a tungsten filament or modified tungsten filament. So this electron gun, you have a different type of emission, that is thermionic emission, Schottky emission, and field emission line. And in this particular case, that okay, when there is a metal ion, how much electron density we are getting from that metal. Based on that, we can classify this electron microscope is a good quality microscope with poor quality microscope. So here you can see that ion density we can calculate from this equation, where A is a constant, it is depending on that metal. If we are using the tungsten, it will vary based on the tungsten and the temperature of the metal. And here one more factor is very important, that is this watt function. What is that watt function? So I want electron from a metal. I want to eject that electron. How do I? I have a metal, I have to give some extra energy. Whatever electron in the periphery region, it can come out. But if it will come out, there will be a charge difference. Whenever electron will come out, the metal will be positive and electron will be negative, it will go. So we need that much energy when electron will come out from the metal and stay nearby, and their velocity will be 0. That is called the watt function of that metal. Okay, so we need that much energy to remove one electron from that metal. So here different metal has a different type of watt function. That means you need different types of temperature or heating to remove the electron. So generally that field emission gun we have something very low heat we can give it, and then we can use the anode to pull out electron from the tip. So here, this is a schematic diagram. I don't want to spend on that part too much. So here you can see a thermionic emission, where you have a metal tip, and then we are using a heating. So generally 3000 Kelvin, we are heating the tungsten filament. When we are heating that much, electron will be come out, and then there is a anode plate which is pulling the entire thing. But you can see the distance between the filament and anode plate is huge. The field emission gun, where the anode is very close to the tip, and very strong electric field will use it to pull out the electron. In that particular case, we don't have to heat that filament too much. And then it will be easy to remove the electron from the cathode part. Now, someone can tell, okay, what is wrong if we just heat for longer time? The main problem is that you can see this tip is a very sharp tip. And now if you heat it more, it will be not that sharp tip, it will be spread all over. And then your electron coherency will go. So your electron beam should be very coherent if you want high resolution images. If your tip is, like this, then definitely it is going to affect your beam coherence. That is one of the problems. That is the reason that field emission gun is much better for the imaging purposes. So this is some images how you can see. I thought I'll bring a tungsten filament to show you guys. The tungsten filament, yes.
Is it the coherency inside the spatial resolution?
Say again?
Is it the coherency inside the spatial resolution?
Yeah.
But in STEM, we have incoherent electrons. We have better emission as compared to conventional.
No. That coherency is not only depend, because look, the one thing is that definitely your filament, how this filament is behaving and how you are extracting that electron. So if electron is coming from that, definitely it will be helpful. But there are some other parameters are also involved. And whatever that aberration you are talking about, those are also involved in your resolution part. It is not about, so this is one of the part involved for your coherency, that, okay, if you less heat, your tip will be very sharp and it will be much easier to get a coherent electron beam. And it may affect in the later stage also, right? Now, this is a tungsten filament, as I mentioned. So this is a very sharp tip, and there is a similar kind of thermionic emission you can see for the lab 6 crystal also. Why? From the tip you can get the electron. Now this is the field emission gun. The field emission gun, generally what I showed you previously, that short speed field emission gun, they are using the same tungsten type of filament, but they are coating with another chemicals that is called zirconium oxide, and they are decreasing the work function drastically, and which is helping as a very low, not very low temperature. But this tungsten filament, if you have to heat 3000, in this kind of filament, you have to just heat 1400, and it will be easy to remove electron. Now it is coming to the electromagnetic lens. So electromagnetic lens, if we just consider that, okay, in entire, if we just consider this is the column of the microscope, your electromagnetic lenses are going like that. Okay, it is a copper wire closely packed. So this, if you have a copper wire, it's winding very tightly, and this is, it is going, if you have a magnetic field will go this direction, because your electric flow is going like that. Now, from the top, from the electron gun, one electron is going to the center, to the optical axis. So there will be no deviation. It is just like a glass lens. If you have one ray is going through the center, if one ray is going through the center, there will be no deviation. Okay, but when there is a electron, it is going through the center, and one electron is deviated from the center, and there is a magnetic field. Okay, so the magnetic field is going this direction, and your electron is coming this direction. So now, if you just remember your right hand thumb rule, so this is your magnetic field, and your electron is going through this, it will push your electron in this direction. So it will be not a straight line anymore. So what I So here, it's much easier to draw like that, the straight line, to explain this thing. But there will be a deviation because this right hand thumb rule, because your electron is going through this and the magnetic field is pushing in this direction. So if you look at this, so this is the ray which is going through the optical axis. There is no deviation, it will just go straight. But there is another ray which is started in this direction, and as I mentioned that right hand thumb rule, if we just place it like that, so there will be a deviation in this direction, and you can see it started bending. The same thing is going to happen when it will come in this direction, it will push towards that. So if there is an electron beam, it will come and it will enter the magnetic field, it will go through like that and converge in one point. So here we can use the electromagnetic lens system to converge the electron beam and the diverge. That is not possible for the X-ray because X-ray we don't know how to converge or diverge. Here we have a charged particle. We can use highly negatively charged particle to converge or the magnetic field to converge them. That is helping us to get an image. So here, just like glass lenses also, you can see there is a rotation is also possible because it is not a straight line anymore. There will be a spiral trajectory, and this spiral trajectory is rotating the image. Okay. Now, there are a couple of types of incident can happen. So whenever there is a light or electron or X-ray, one possibility is that it can absorb by the medium. And then second possibility is that if there is a nearby electron, there will be a scattering. Third, that is the deflection is possible, that if it is close to the nucleus, it can deflect in a different. So then reflection is possible, that is, any mirror, and refraction for the glass lens. So in electron microscope, most of the time we are considering the scattering because we are talking about the transmitted electron beam. And I wrote these things couple of times that light is not damaging, but X-ray and electron is damaging. Why? Because here you can see this media can absorb that. When there is a high energy electron, it will absorb, it will start damaging the sample. It will start damaging any body. So if it is a graphene or any material science or any metal, that gold, silver you want to see, you cannot see that much problem. But for a soft material or the biomaterial, it is very problematic. Yes.
So how much time it takes to damage? Like, what is the time duration of for an electron beam to damage the sample?
So that is sometimes it is very difficult to tell that how much time it will take. Generally, it will just consider in our case for I'm just giving an example that material science generally they are using electron dose 400, 200, 300, 400 electron dose per angstrom square per second. For biological cell sample, we are using only 40 electron per angstrom square. It is in 10 seconds. You understand? If we just use the 400, I don't know. So sometimes that you have a gun, and if you just shoot in a glass, and it will be heavy speed, high speed, it will just make a small hole and it will go. And if there is it will get little bit time to transfer its energy, it may probably break the entire glass. So it is something like that. Sometimes it depends on the ice thickness also, and also how much electron dose you are using. So if you use what we notice that this is our practical experience that okay, you are using 40 electrons. Generally 10 seconds is okay, that there will be not too much damage, but still damage will be there. We cannot say damage will be not there. Okay.
And what is the spot size where the damage is? Spots, I mean, the sample is there. So how much is this? Like the whole sample will be damaged or
that will I'll come. So sample related thing when we will talk, that time we will discuss that one. So here you can see this is an atom. Okay. So one electron, there is no scattering, no interaction, it is passing through the atom. And this is always good. It is not interacting, it is something like that. We have, some friends, they don't want to talk to anyone. They are staying their own and checking the cell phone and just eating and going back to the room. It is like that. They don't want to interact with anyone. So they are not creating any problem or not creating any happiness to anyone. So they are their own. So it is something like that, the unscattered. Things are changing when there is some electron field are close to other electrons. Okay, so then what will happen? They will just start deflecting from their original position. That is called the scattered electron. So as I mentioned previously, that we always like the scattered electron, because that scattered electron at the end, it will give us the phase contrast for our images. Okay, so this scattered electron is always good, and when there is a scattering, there is no interaction with the electron here, and that is the reason they are not losing any energy. There is no direct collision between those electrons. But there are some cases the incoming electron is just going to hit directly to any other electron, and then they will displace this electron position, and then they will lose the energy. When they will lose the energy, that is called inelastically scattered electron, and they are very problematic. They will create noise. Why? So if we just think about why. So we are talking about electron energy, and we are considering all the electrons are coherent, all the electrons are coming in same energy and giving us an image, because we are using a magnetic lens. Now, when we are using a magnetic lens, its power is same. We cannot change the power. And when the electron is not losing any energy, they will come and they will convert somewhere here. When they will lose energy, they are not that strong anymore. And if we use the same magnetic field, they will convert somewhere here in the same image. And then they will create a problem, then they will just create a blurring effect. That is the reason inelastically scattered electrons are very problematic, that better to avoid. But we cannot. For biological sample, definitely we cannot do that, because there are so many atoms are there. How do we control those things? I'll just skip this one. There's no point. Now I'm coming back to the sample related things. Okay. So here you can see that, okay, how we can use this electron microscope. Now probably you guys will be a little bit happy that he is constantly talking about, I think, magnetic lens. So how we can prepare our sample. There is a different types of grids are available, but most of the cases, the grid diameter, it is 7. It will be 3.05 millimeter, that diameter. Now, there is a 2 types of microscope we can use it nowadays on majorly. Oh, one thing I forgot to talk about. Sorry. Here you can see there are some incident electron. They are very close to nucleus and going back. And that is called the backscattered electron. And sometimes what happens here, when there is an electron, it will hit the electron and they will displace and they can go back also. Those are called the secondary electron. The secondary electron and backscattered electron we can capture. And that is called the scanning electron microscope. It is not transmitted to your atom, it is just scanning the surface. Okay, so that is the reason this electron is also very helpful. Okay, so now we are doing room temperature temp. So whatever that material science sample, if you just consider that you want to see the graphene, you want to see the graphene oxide or any metal, we are generally using the carbon coated grid. So here you can see those squares. So if I just go to the next step, here you can see those are the metal bar. Generally those are the copper bar. And then on top there is a amorphous carbon layer, because you need some platform where you can add the sample. And then if you look at this particular square, you can see there is a platform, you can add sample here. And then you can image it. You cannot make anything very not transparent thing. So whatever is required, you need that amorphous carbon layer kind of thing. So your beam can transmit it through that layer. If it is not transparent, then it is going to block your sample. Generally, thickness will be only 15 to 20 nanometer, not more than that. Okay, there is another type of grids are called, that is called the holy carbon grid. What is that thing? That is mainly for cryo-electron microscopy for biological sample purposes. We are using this. We also have the same kind of square here, and then we also have same kind of carbon layer. But the only difference is there is a uniform sizes holes are there. That sample, the bio sample will stay inside that hole, and then we are trying to image those samples. So this is the enlarged view of this one. So I'll come back to your point here when we will discuss that. So this is the how we can do the negative staining. So here we are just looking at one small square, and this is the carbon layer. And now if I just draw this schematic diagram, that this is the metal part. So from this one to this one, and this is the carbon layer. And we added the sample. When we added the sample, we have the 3D structure in a biological sample if we just consider. And this is the buffer solution. Then we are blotting the excess buffer, because inside microscope, electron microscope, whenever we insert, there is everything should be under vacuum. That thing I forgot to tell. That three things is different from light microscopy. One is that light source, it will be electron, and then electromagnetic lens, not the glass lens. And the electron microscope is always will be in a very high vacuum. Why high vacuum is required? Because otherwise there will be a collision between air or any moisture, and then they will deviate from their position. That is the reason we need. So here you can see the biological sample, and whatever excess solution is there, you have to blot, you have to make it dry. Otherwise, if you put it inside the microscope, it is under vacuum, and it will just, moisture will evaporate and it will crash the system, and your filament will be damaged because your moisture will deposit there. That is the reason you have to make it completely dry. Okay, now we are using a heavy metal staining solution, either uranyl formate or uranyl acetate. So uranium is 92, and this is not the radioactive one, it's the depleted uranium we are using. So heavy metal staining solution we are using to stain this sample, and then finally we'll blot it, we'll dry, and then when electron beam will pass through this, you can get a 2D image. So here you can see when there is a 3D structure, it is when you blotted everything, it's completely dry, it is basically collapsed. It is not its original position. So that is the reason here I mentioned that most of the time you can check the homogeneity and size of the sample, concentration. The contrast is always very good. You can use any kind of electron beam because it is sample is completely dry sample. And now easy and quickly you can get the data. Here you can use it for any kind of biological sample. The major problem is that sample is not in physiological condition anymore because it is completely dehydrated. Waters are going out. So now here you can see those are some of those images we collected in our facility. So one pore-forming toxin that I told that host-pathogen interaction we are interested. So there is one of the pore-forming toxin image. This is one of the metabolic enzyme. So those whites are the particle here. Okay, and then there is some SARS-CoV-2 spike protein we also characterized in our lab. Those are measured. So now you can see the cryo-EM sample preparation. That is, you have a cryo-EM grid, and this is the enlarged view. So as I mentioned that in cryo-EM, the same carbon-coated grid, you can see that hole. What we are doing, we are using a vitrobot, we are adding sample here. We plot the extra sample using this filter paper. I have a video, I'll just show you that how to do this thing. Then when you quickly plunged into liquid ethane, it will form an amorphous ice inside that hole. Okay, because you cannot keep your sample in solution and it cannot pass the electron beam to see it. Then you will start moving around, and also the vacuum is another problem. We have to fix the sample. Whenever you are putting something in liquid nitrogen, it will form an ice, it will form an amorphous ice, and your particle or things will be fixed there. Then it will be easy to image. And now the good thing is that it is not dehydrated, it is in frozen condition, right? So we are targeting the individual holes here. Okay, if we look at this individual hole, what we will see, as I mentioned, you will see a amorphous ice layer. Within that, the protein is embedded. So you have you are baking a cake and you have creams or nuts, you are putting it, and it has a different orientation. Same thing. It is just you consider that it is a cake and the protein is a different orientation. Now, when electron beam will go, you will get a 2D image of this. Now, you take this 2D image. This is the very time consuming thing. So we cannot explain it in one class. So what we'll do, you have the individual protein molecules here. Okay, we pull out them. We classify them in a different group based on their orientation. So if you just same hand, if I take your left hand, my left hand, so someone's this will be smaller, someone will be bigger. If we just same category, we will put it together and classify that, okay, this is one category, this is the second category. So this classification, generally we are using the K-mean cluster, okay, to classify those particles, and then we get the 3D structure from that. So we'll not talk about this one today. So here I'm just quickly show a sample preparation part that how we are doing this thing. So we have a grid here that I told that copper grid we are using. So this is the area where we have the liquid ethane and liquid nitrogen is surrounding area. Then we'll add very small amount biological sample and quickly plunged into liquid ethane. So here we have the grid and then we add our sample here, and generally we use a very small amount sample. So this is the place where we are going to add the sample. I'll skip couple of slides. So we are adding this sample here. Then using this blot paper, this entire thing is happening automatically. Here we are doing nothing. So then filter paper will blot. How much blot time, how much blot force, that we have to decide at beginning, and then we'll freeze the sample. So you will get a frozen grid. When we have this frozen grid, we'll transfer this frozen grid to microscope for the imaging. Okay, we'll skip this part. Okay, at this moment this is not required. So I already discussed about that cryo grid preparation, sample loading. Now I'll talk about this imaging part, how we can image. So here you remember that, as I mentioned here, that okay, you have an amorphous ice here, right? Ice means ice, and electron has a very fine energy. And now any microscope you have to focus. How do you focus here in this ice? At least when you try to do a focusing, it will take at least 30 seconds, even if you are very fast. Generally, we are taking that we just want 8-second exposure, and if you start focusing here, that will damage the sample. That is the reason we are using a tool where at a very low mag will select some holes. That okay, I want to image here, I want to image here, I want to image here. And those holes I want to avoid because there are some black patches up there. So we'll target those holes for the imaging. And when we'll focus somewhere outside the amorphous ice. And then automatically we'll come back our required area and collect the data. That is how most of the time in cryo microscope we'll collect the data. So I don't know, do we discuss about this one? So look, so any microscope that is, previously also I was thinking that when you are talking about focus, that is basically not actual focus, because our eye is comfortable with that part. That's why we are talking about, okay, this is the focus. Okay, so if you look at this video, that will be much more clear. Okay, so here I'm just showing you some material. Okay, And this is actual focus. If you just consider this is the actual focus. Now I'm slowly, gradually changing the focus value. So what we can do either a over focused or under focused. And whenever we are doing the over focused or under focused, you can see some outside that fringes are very much clear. At early stage, when we are at focus, we cannot see this object in so much details. But whenever I'm changing the over focus or under focus, you can see these fringes are very much clear and contrast is improving. And that is helping us to see this object. So that is the reason I'm telling that, okay, whenever we are talking about, okay, this object is in focus, that means it is either over focused or under focused. It is not the actual focus. Okay, so this is how, we have to consider that what, what kind of focus do we want? That we want a over focused image or an under focused image, because that focus, the same image, if you just consider that those are my protein molecules, and if something is under focused and if something is over focused, the same thing is looking different. That is the reason in, especially for electron microscope, if you just don't collect our data properly, same thing can appear in a different way. If you just change your T-focus, that if you are using under focus and then same thing if you are imaging at over focus, your sample will look completely different. That is the reason we have to be very careful when we collect the data. Okay. Okay, let me move little bit fast. I'll skip some of these slides. Okay, now here you have something that you are asking that, okay, what should be the spot? So when we are imaging something, we want a diameter somewhere, so which should not expose this entire area. So our sensor level of this K2 camera or CCD camera, whatever we are targeting, that as I mentioned that whenever you want to focus, you want to focus in outside, not inside here, because if you start focusing, it will melt the eyes. So now our spot, whatever we are targeting only this much area, not bigger than this one. Okay, so that we can adjust that, okay, what should be beam diameter? So we should not say the spot size, because same spot size we are using for the condenser lens 1. The spot size will, help us to determine how much electron dose are coming. So here we can say what is the beam diameter. Generally, beam diameter, you can consider that 1.6, 1.62 micrometer should be the beam diameter. So it should not expose the entire hole also. Okay, so that is the condition. If you just keep it for 8-second exposure and 40 electron dose per angstrom square, that will be good enough. If you just stay longer, something, 10 seconds or 12 seconds, it will start melting, but it also depends on the ice thickness. That is why I'm going to come in the next one. So ice thickness is a very important part, because what kind of things we want to see. If we just consider that I want to see a protein molecule, it is a 5 nanometer size, and your ice thickness is 100 nanometer or 200 nanometer. How do you see that one? And exact result will be something like that. You cannot see anything. I cannot see anything, so I can see some large thing. Now I want to see a virus particle or a liposome. That always stay near this carbon area, because you can see the thickness of the ice is much higher here. So if you look at this liposome, this virus particle, so they are always staying near this carbon. This is the carbon and this is the ice starting. So here I am showing you some more virus particle. So they are very close to this carbon area, because thickness is much higher. Because that thickness is also required to keep your sample there. Otherwise that will be damaged. So now if your ice thickness is changing, you can see that when there is a very thin ice, particle will go away from the center area. So exactly that is happening. It is pushing all the particles towards the edge, and the center part is completely empty. Okay, so that ice thickness is the important role that, okay, that we have to control. That is the main bottleneck. That, okay, what should be my ice thickness, and that comes to the sample preparation part. So here, this is some of these images that everyone will be happy to see that. Okay, those are the virus particle, and here there is the adenovirus. This is the bacteriophage. So this is I just imaged for a thermometer on the nice side, and I just showed this image here because it's looking very nice. You can see the phage tail also, and the DNA is coming out. And then you can see some of these bacteria, Professor Dikshita Chakravarti, some of these bacteria we imaged in prior condition. Basically, I don't know, I don't do bacteria or virus sample. That's why I just have to borrow those images from other places. So here you can see a bacteria, you can see the flagella. Here you can see the pili also very clearly. All this pili. Okay, so you can see flagella, pili. That you cannot see it in any other microscope. Okay. Now, I'll just quickly talk about little bit about my own interest, and which is not be connected with too much about what is called the bacteria viruses. We are always dealing with a protein or DNA protein interaction or RNA protein interaction. So a couple of examples or case studies you can say. So our main interest is that host pathogen interaction and how it is interacting with the biomembranes. So previously, whenever we are doing structural biology, if you consider that X-ray, NMR, something, you cannot see the liposome or the host cell, because host cell means first thing will come to our mind that lipid membrane, because wherever we see there's a lipid membrane and then cell or bacteria or something is attacking. We want to see that, and electron microscope is the best tool to visualize the lipid and then your protein and then get the structure with those things. So here, this is, we recently resolved a lot of structures from our facility. So almost around 50 structures. So this is the SARS-CoV-2 spike protein with the inhibitor. There is a spike protein structure only. This is the spike protein with antibody. There are some RNA protein complex. This is HIV trimer with antibody. So those are some core-forming toxins and other toxins that we characterize from our lab. Now, this is one of the spike protein we characterized during the COVID time. It is just after lockdown we got permission somehow to work because we are working on this SARS-CoV-2, and there we got the purified protein from Professor Raghunathan, and we characterize these things. And here you can see this is a very nice data that negative staining. We can see individual protein molecules, and then this is the cryo image. There is one difference. Can I ask one question? So both are collected in temp. One is in cryo temp, one is in room temperature temp. One case it is same sample, it is appearing white, and other case it is appearing black. The protein, those are the protein molecules in cryo. White. Stacking is there, both the cases. One case we are using staining solution. Here, heavy metal staining solution. Here we are not using anything. Here it is in buffer. And now if you just consider buffer or water and your protein molecule is more dense than your buffer. That is why background is comparatively white and your proteins are appearing as black, because scattering will be more due to protein. And here this is just opposite, because the heavy metal staining solution. Okay, that is the reason I put both the image side by side, so I can explain that. Now we resolve the three-dimensional structure of this spike protein, and there we showed that okay, physiological pH is very important for this open conformation and closed conformation. And not only that, we are getting open or closed conformation, we are getting some intermediate conformation also. So I don't want to spend too much time with those things. Here also, one of the enzymes we characterized from the microchem tuberculosis. This is a very important enzyme which reduces the oxidative stress, because cysteine is the amino acid, while we have a sulfur. Whenever sulfur oxygen will be there will be an oxidative stress will be there, and bacteria cannot survive. So bacteria want to reduce that, bacteria want to remove that hydrogen sulfide. This is one of the enzyme which is involved, which is just remove that sulfur from the cysteine as a hydrogen sulfide. So in that particular enzyme, it was not characterized the entire tertiary structure. Here you can see we dissolve that tertiary structure, which is appearing as a tetramer. 4 protomers are connected. Not only that, in that one, we find out the mechanism also, how it is interacting with the pyridoxal phosphate. So initially, the active site is interacting with the pyridoxal phosphate, then it is removed, substrate is coming, and it is just like a movie, we can capture all the state. And that is very fascinating that, okay, so one particular small enzyme, how it is interacting one by one substrate and how it is changing from one conformation to other conformation is a very interesting thing. At least it's a very, very interesting thing for me. So here, one of the part where I told that lipid protein interaction, post pathogen interaction. This is a toxin molecule. This toxin molecule can bind to the lipid. So these are the lipid bilayer where you can see in some cases it is completely empty, no protein is there, and some cases it is completely decorated by protein. So here you can see there is a two lipid bilayer is clearly visible. The electron microscope is the only tool where you can do this kind of images. No other tool you can use it. So here you can see the lipid bilayer as well as that all these barrel, it is very clearly visible from your 2D images. So now when we have this kind of data, we determine the structure as well as you can see we capture the flexibility of okay, so here you can see this barrel part is changing in presence of lipid. It is breathing. We capture all this barrel one by one. That okay, when it is inserting through this lipid, can we capture this? That is one of the main interest for this project. We capture the entire thing. Okay, so this is, I'll just keep this part also. Is that okay? Huh? Okay, so this is also another project that we are working how one of these protein can interact with the mitochondria and damage the mitochondria. So here we just did the structural characterization and we can see that mitochondrial lipid it is binding with this mitochondrial lipid. So I'll finish my talk here. Couple of things I just want to tell you that okay. So take home message that okay, take home message should not be from my own project. Message is that I believe electron microscope is the only high resolution method is available so far. Okay, there are so many other microscopes is there, but I do this thing and I really love it. So, and also you can use it for structural characterization in physiological condition. So this is my group. They are just finished their PhD and now doing the postdoc. And this is our cranium facility. And here there is a huge user list. Roughly 70 to 75 users almost every year. And sometimes you can consider some labs you have 2 to 3 students are using. So that number is huge. And whenever we are collecting data and those things, generally we need a 24/7 data collection, at least for 2 to 3 days. And I cannot say that our facility is used by Kashmir to Kanyakumari, but I can definitely tell that it is used from Jammu to Trivandrum and from Ahmedabad to Kolkata. So that is the current situation. And it is open for everyone. I encourage people to use it, any student and researchers. Is all. Now, if you have any questions.
Yeah, so if anyone has any question, they can ask.
So, let's say, anytime we want to see what is going on with respect to time, like light television and all. So here, and we are freezing the sample, so we are not able to see that now what is going with respect to time. What is the changes? Yeah.
That would be because whenever is freezing, you are freezing a sample. In that particular moment, if there is a different confirmation, we'll trap that one. That whatever I'm showing that spike protein, right? We trap that one because that receptor binding domain, it has a continuous motion. So it will be not like that always close or open conformation. Some intermediate stage are also there. We fetch all these things together and we get it. But the time dependent thing, it will be a difficult thing, but nowadays there are many new things are coming, new techniques are coming, the freezing sample also. That you are not mixing the sample in a appendix tube, you are just taking the sample and mix it in the grid just before freezing. And that when reaction will go, that time you will freeze. So then you can see the time dependent thing. So that time resolved timing is one of the important thing nowadays, the new development that people can use. Another drawback is that you cannot do any live celebration because inside the microscope it is high vacuum. So no living object can survive there. So that is one problem.
So, right, if
Yeah.
Let's consider a protein which has some ideal structure. When you prepare a sample, due to that freezing, can that structure change slightly? Is it possible?
So slightly change means, look, if you,
Will it look similar to the ideal structure?
yeah, it should. It should if it is in a natural situation. When I was showing you your ice thickness, do you remember? There are many times protein has a tendency to stay that air-water interface. And when there is a air-water interface, they will start denaturing. And if you just focus on that, definitely it is going to affect your structure. So that will be not the ideal situation. So that is the reason whenever you collect the data, it should be in a proper condition. So here, whenever you are freezing something, you are freezing something in a very rapidly. There is, fraction of a second, everything is frozen. So structural change will be not there because of the temperature change. That is for sure. Okay. The problem it will come that air-water interface or something else, that mishandling, that okay, if you have a lot of crystalline ice and your structure is just, punched from different orientation by this crystalline ice, then definitely structure will affect. Otherwise, not.
okay,
What is that? So you have this treatment. So generally, so the electron
Electron. So generally we are using tungsten filament. Tungsten filament is the thermionic emission. Then tungsten filament, when you coat with zirconium oxide, that is called the X-ray. And there is, I told you some purple crystal, right? That is lab 6 filament. Lab 6 is lanthanum hexaboride or cesium hexaboride. That crystal we can use it.
how sharp is that?
No, I don't exact in millimeter how sharp I can say.
So let's say instead of that, we use iris, like iris signal. So we can make an aperture which is smaller. Can we get similar function?
I think it depends upon how sharp it is. So maybe it is somewhere between, somewhere about in microns,
Yeah,
few tens of microns.
Yes.
How sharp it is.
yeah.
Because that decides how much focus is going to happen and how good the image will be. Okay, if no, I have something to ask. I mean, first of all, it's a great talk and quite in depth and a lot of elaboration on this. And I think, a lot of first timers actually are going to like this talk because they're going to learn a lot from it. Okay. It's also, of course, it is available on YouTube and it will be on YouTube for world scientific community to have a look at it and to learn from it. Somnath, I have just something to ask you. Where do you see the future of cryo-EM and what kind of biological problems which are actually still not tackled are going to be tackled in coming days? I mean, what is the kind
So
of?
look, I believe that in cryo microscopy, you can use it for what I showed, that is the single particle analysis, that you have a purified sample and you are taking it and you are tracking it. Now micro-ED is also coming the same instrument. You can use that microcrystal and get the crystal data. And another one is the cryogenic tomography, that you have the entire cell. And then something is attached and you are doing the structure. So definitely nowadays some labs are getting high resolution, but a lot of improvement is also required. And okay, you have the entire cell. And I believe that next 10-20 years, that will be the only tool available for
Yes, yes.
getting the high resolution.
But
So you can do the cell biology related work, you can do the imaging as well as you can do the structure.
Mhm.
And you can get all the details from a 50 nanometer resolution to,
Correct.
1.5 angstrom resolution. So that is great.
So I guess you can use it in cell biology as well as disease biology.
Yeah.
I mean, all kinds of, so it is going to penetrate, I guess, the physical sciences as well, right?
Definitely, there are many, chemical sciences
Mhm.
or physical sciences people they are coming. So something like that, some amyloid formation is there. So
Material science.
material science that okay, sometime in battery there is some extra code and there is some kind of amyloid. So what kind of works are there, also we can visualize.
But anyway, it is a great talk, let us thank you. Thanks a lot for this. Yeah. So.
We are done.
Yeah.
Now we are.
Okay, so now we can go for lunch. Lunch is ready.